Today we will see lift on an aerofoil or airfoil. Yesterday we have learnt what is Kutta-Joukowski equation. The same may be used as an application in case of aircraft wings, that is aerofoils, blades of propellers, even it can be used in case of pumps and turbines, etc. Now, an airfoil is a streamlined body which may be either symmetrical or unsymmetrical, as shown here, may be symmetrical or unsymmetrical, which is characterized by one, chord length C, chord length C, span L, angle of attack alpha, and aspect ratio AR. These things you can see in the figure. This is chord line, the line joining between the trailing edge and the leading edge, whereas camber is the vertical height between the camber line and the chord line, whereas alpha is angle of attack. It is the angle between the line parallel to the liquid flow or fluid flow and the chord line, which is shown in figure. This is symmetrical, this is unsymmetrical aerofoil. This is the chord length C. The span L is the total length of air wing in the direction perpendicular to the chord line. Okay. Now, expression for CL on an aerofoil, and then we can find FL and FD, that is lift force and drag force on the aerofoil. Consider a uniform flow of ideal fluid passed off an aerofoil. Then the flow pattern is as shown in figure A here, that is translation. Now let us import a circulation around the airfoil. Around the airfoil a circulation is imported, then the flow pattern will be as shown here. Now further we superimpose these two as we did in case of a sphere and as well as cylinder, then the combined pattern will be shown. The combined pattern, that is translation and circulation, is shown here. In this figure, this is the tangential line. This is the tangential line that is to be produced by controlling over the circulation while importing on the aerofoil. Now, by making use of the application of Kutta-Joukowski equation for any shape of the body, it is possible for us to find out CL on aerofoil. From theoretical analysis, it is shown that by proper control of circulation, it is possible to adjust the flow pattern in such a way that the streamline at the rear of the aerofoil can be obtained tangential here, tangential to the aerofoil. In order to do so, or while doing so, the circulation which is required to produce such a tangential line, analytically it is given by circulation is equal to pi cu sin alpha, where c is the chord length, where u is the uniform velocity of flow and alpha is the angle of attack. Now substituting this value of circulation in the lift formula given by Kutta-Joukowsky equation, we have FL is equal to rho u LT, rho u L, this tau, that is circulation, we can write it as pi Cu sin alpha. Therefore, we will get pi Cl rho u squared sin alpha. Now, multiplied by 2 and divided by 2 and rearrange the equation, we get 2 pi sin alpha multiplied by L multiplied by C multiplied by rho u squared by 2. So, we shall combine 2 pi sin alpha together, L and C together, rho u squared by 2 as it is. Then FL we can write it as, in place of 2 pi sin alpha, we can write in this general form CL multiplied by LC multiplied by rho u squared by 2, where LC is nothing but area of aerofoil. Therefore, CL can be taken as 2 pi sin alpha. This is the magnitude of CL on an aerofoil. This is a very good application of Kutta-Joukowsky equation which we have derived in the last class. Do you remember? Okay. Then further, the lift coefficient and drag coefficient can be obtained in the laboratory by performing an experiment on any aspect ratio of aerofoil in using wind tunnel. Then we can plot the curves like this: CL, CD on y-axis, angle of attack alpha on x-axis. Then we get, this is the curve for CD versus alpha, the bottom one or the top one. Similarly, now CL versus alpha is this curve. Okay. Now this curve, this dotted line curve is theoretical curve of CL, that is nothing but equal to 2 pi C sin alpha. Here you can see 2 pi sin alpha. 2 pi sin alpha is the theoretical CL. We can observe from this figure the theoretical curve and the practical curve for CL for various values of angle of attack. They resemble with each other up to 7 degrees. Alpha is equal to, up to alpha is equal to 7 degrees. There is no change. Both are in the form of a streamline curve. Whereas after 7 degree, about 3 degrees, that is up to 10 degree or at 10 degree of angle of attack, the value of coefficient of lift is maximum, and then it starts decreasing, that is due to separation of flow. You can see this maximum point where the CL is maximum, we call it as stalling point or stall point. Corresponding angle of attack, that is alpha is equal to 10 degree, is known as stalling angle. You can see here, stalling angle. When alpha is greater than 10 degrees, it is known as stalling angle. Now, there is no much variation of CD with respect to alpha, as you can see from both these two graphs, upper one, lower one. There is no much variation as far as the value of alpha is concerned. Only after 10 degree, because of separation of the flow, there will be value increase in the CD value only after 10 degrees, that we can observe. Okay. Further, the efficiency is given by CL by CD. The ratio of coefficient of lift to coefficient of drag is called as efficiency. Now, last article in this first unit A is polar diagram. Now, as we have already said, the laboratory experiment in wind tunnel using a particular aspect ratio of aerofoil, say L by C is 5, where aspect ratio is nothing but span to chord length for particular angle of attack alpha. So alpha value varies. When this particular aerofoil is subjected to test in wind tunnel in the laboratory, we can evaluate CL, CD, coefficient of lift and coefficient of drag. Now we can plot the curve as shown here, which is suggested by Prandtl, Prandtl, suggested by Prandtl to combine three curves as a single parabolic curve. You can see here, single parabolic curve is known as polar diagram. We have more use of this polar diagram by constructing three graphs, CL versus CD for different angle of attacks along the curve itself. You can see along the curve there are so many angle of attack values for which CL by CD curve is plotted. Also the ratio CL by CD, that is efficiency, can also be plotted simultaneously for corresponding values of angle of attack, say -8 degree, -6 degree, -2 degree, +2 degree, +4 degree, +6 degree, etc. as shown. Then the use of this polar diagram is, or first of all, the coordinate of this polar diagram is CL and CD and angle of attack along the curve itself. Now we can draw the theoretical parabola. The dotted line shows, this dotted line shows the theoretical parabola. Both have streamline up to certain value, and then as we know, because of the separation of flow, coefficient of lift decreases. That is also is shown here. After a particular value, the CL value is decreasing up to certain value. Both theoretical and as well as practical curves resembles with each other because they are streamlined. Now, major or important use of this polar diagram is the ratio of lift to drag, that is efficiency of any point. Suppose if I consider this point, I want efficiency, then I have to join this point to the origin. The slope of this line joining the origin and to that point is nothing but efficiency at that point. Suppose if I want the maximum efficiency, then I have to join from the origin to the maximum point on the curve, that is as a tangent. The tangent line drawn up to the origin, the slope of which tangent line, this is tangent line. This tangent line, when it joins origin, we get maximum efficiency. Also this polar diagram shows zero lift, minimum drag value and maximum lift to drag value, that is the tangent point on the curve. So this is complete as far as unit 1A is concerned. Let us stop here and we will continue with numerical problems in the next class.